My talk today is on the separation of mixtures of ethene and CO2. Most of the adsorbents are selective to CO2. A particularly interesting case of mixture adsorption is LTA-5A Zeolite, in which the adsorption of mixtures of ethene and CO2 show selectivity reversals. For mole fractions of CO2 in the bulk gas phase lower than about 60%, the adsorption selectivity is in favor of CO2, but for mixtures in which the CO2 mole fraction in the bulk gas phase is higher than about 70%, the mixture adsorption favors ethene. The ideal adsorbed solution theory does not anticipate the adsorption selectivity reversal and predicts that the mixture adsorption is selective to CO2 for the entire range of mixture compositions. Now, the experiments that I plot here, shown by the red circles, are from the paper of Basmarjian in Canadian Journal of Chemical Engineering 1980. I've reanalyzed their experimental data in the two papers I list here, wherein I show that for explanation and modeling of mixture adsorption, we need to abandon the IAST theory and we need to introduce the quantification of thermodynamic non-idealities in the mixture. Just to remind readers, 5A zeolite is LTA-5A, Linde type A zeolite. It consists of a structure in which we have cages of about 11 angstrom in diameter, and each cage is separated from adjacent cages by windows that have apertures with dimensions of about 4 angstrom to 4.58 angstrom. It is a misconception to think that a 5A zeolite has a window aperture of 5 angstrom. It's just a rough indication. This is a cation exchange zeolite. 5A is a cation exchange zeolite, and one unit cell of LTA-5A zeolite consists of 32 extra framework sodium cations, 32 extra framework calcium cations, and further details of the structures of these zeolites are available in these papers of mine. See also videos of azeotropic adsorption, selectivity reversals, the real adsorption solution theory, and the IAST on my YouTube channel. Now, why do I wish to focus on these selectivity reversals? And why is the separation of mixtures of C2H4 and CO2 of industrial importance? This is because in the oxidative coupling of methane process, the products of the reaction contains several components, including ethene and CO2 with ethane, methane, nitrogen, and other components. It is of importance industrially and economically to selectively adsorb ethene. As we note from these mixture adsorption experiments of Basmadjian, LTA-5A zeolite becomes a candidate for feed mixtures that are poorer in ethene but richer in CO2, as is the case for the OCM products, as I will explain in the subsequent slides. In the process for oxidative coupling of methane, OCM, involving reaction of methane with oxygen on high temperatures, the reactor effluent consists of a mixture of hydrogen, methane, carbon monoxide, carbon dioxide, ethene, and ethane. There is considerable economic incentive to recover ethene from this reactor product. Use of PSA technology for recovery of ethene offers the potential for the development of an energy efficient OCM process. The optimal scheme for implementation of PSA technology requires the use of an adsorbent that is able to selectively adsorb ethene from this product mixture. Specifically, we require an adsorbent for which the selectivity of ethene with respect to carbon dioxide is significantly high. Of the potential adsorbents, activated carbon is perhaps a cost-effective solution, as concluded in this publication. In this process scheme, say using activated carbon, the extract phase containing ethene plus carbon dioxide and ethane can be led to a CO2 removal unit, say using amine absorption, and the recovered ethane mixture can be distilled to produce pure ethene. The bottom's product containing ethane can be used as a purge gas in the countercurrent desorption operation. The raffinate from the adsorption cycle can be recycled to a methanation reactor whose product is then led to the OCM process. For recovery of ethene from the reactor products in the OCM process, we need to have adsorbents that are selective to ethene, especially with respect to CO2. This is the crucial separation that is encountered. Let us screen the adsorbents for ethene CO2 separations by examining the adsorption selectivity as a function of mole fraction of ethene in the bulk gas phase mixture. The most selective adsorbent is Mn2M-DOBDC from Jeff Long's group at the University of California in Berkeley. Surprisingly, the second highest selectivity is achieved with activated carbon. The other adsorbents, such as calcium X, 13X zeolite, LTA-4A zeolite, and LTA-5A zeolite, are selective to CO2 and not to ethene, according to IAST calculations. The same conclusion can also be drawn from a diagram that plots the mole fraction of ethene in the adsorbed phase as a function of mole fraction of ethene in the bulk gas phase. We need adsorbents that are in the top left corner of this diagram. I examine now experimental breakthroughs for two of these adsorbents, activated carbon and LTA-5A zeolite, as reported in this paper published in Separation and Purification Technology 2020. The choice of activated carbon is understandable because the IAST calculations show that activated carbon is ethene selective. However, the IAST calculations show that LTA-5A zeolite is selective to CO2 over the complete range of feed mixture compositions. I would like to demonstrate that such IAST calculations for 5A zeolite are misleading because the mixture adsorption equilibrium is subject to strong thermodynamic non-idealities that are not captured by the IAST. Using activated carbon as adsorbent, 4 different breakthrough experiments were conducted, and these are reported in this paper cited here. These 4 experiments are with varying proportions of ethene and CO2 in the feed mixture. This is a feed mixture that is richer in ethene, and the ratio of ethene to CO2 in the feed mixture is 3.2. Here the ratio of ethene to CO2 is 1.7, the ratio of 0.85 for ethene to CO2, and the last experiment is for feed mixtures that are richer in CO2 and poorer in C2H4, and the ratio of C2H4 to CO2 is 0.4. the feed mixture consists of ethene, CO2, argon, and nitrogen. The argon breakthroughs are shown here. There's nothing remarkable to note here. And the nitrogen composition is just the remainder of the composition, and it's just an inert. It has little or no effect on the breakthroughs of the other guest molecules. We note that in all cases, the first component to breakthrough is CO2. You can see the breakthroughs of the red circles here. And the last component to breakthrough is C2H4. This implies that C2H4 is the component that is most strongly adsorbed, and the adsorption selectivity of C2H4 to CO2 is larger than unity for all four feed mixture compositions. The breakthroughs with LTA-5A zeolite have a strikingly different characteristic. Here I show the experimental breakthroughs for four different feed compositions in which the feed ratios of C2H4 to CO2 is maintained at 3.4, 1.8, 0.9, and 0.75. For feed mixtures that are richer in ethene than CO2, the component that breaks through earlier is C2H4, indicating that the adsorbent LTA-5A zeolite is CO2 selective. The situation is quite different for a feed mixture in which the ratio of C2H4 to CO2 in the feed mixture is 0.9. In this case, we see that the breakthroughs of CO2 and C2H4 occur at the same time. This indicates the phenomena of adsorption azeotropy, and the reasons for this azeotrope formation is discussed in the video presentation, Adsorption Azeotropy Explained, that is available for viewing on my YouTube channel. If the feed mixture is richer in CO2 than ethene, we see that the component to break through earlier is CO2, and the component to break through last is C2H4. In other words, we have a situation in which ethene is selectively adsorbed from the feed mixture, provided the feed mixture is lower in composition with respect to ethene as compared to CO2. So we have selectivity reversals. The selectivity reversal phenomena is explained in this video presentation that is available on YouTube. Clearly, the IAST does not anticipate this characteristic, as I shall demonstrate in the subsequent slide. For the breakthrough experiments with LTA-5A zeolite as adsorbent, using a feed mixture in which the ratio of C2H4 to CO2 in the feed mixture is 0.75. I compare the breakthrough experiments with breakthrough simulations in which the mixture adsorption equilibrium is determined using the IAST. The breakthrough simulations using the IAST are shown here by the continuous solid lines, blue for ethene and red for CO2. The IAST anticipates that the last component to breakthrough is CO2, whereas in the experiments, the last component to breakthrough is C2H4. So the IAST does not anticipate the selectivity reversal phenomena that is a characteristic of CO2 capture with cation exchange zeolites, as I have explained in several publications. 3 of these are listed here. You may refer to these publications for quantitative appreciation of the phenomena of selectivity reversals and why they occur. I also explained this in my YouTube video, Zeotropic Adsorption Explained, that you can view on my YouTube channel. If we incorporate thermodynamic non-idealities and carry out breakthrough simulations using the real adsorbed solution theory with the fitted Wilson parameters, the breakthrough simulations shown by the continuous red lines and continuous blue lines are in good agreement with experimental data. 2 important conclusions that emerge from these presentations are the following. For recovery of C2H4 from the products of the OCM reactor, we need adsorbents that are selective to ethene, and the crucial selectivity is of ethene with respect to CO2. Activated carbon is a candidate adsorbent. However, the experiments reported by von Zandvoort and others, including myself, and reported in Separation and Purification Technology in 2020, show that LTA-5A could also be a candidate adsorbent, provided the feed mixtures are significantly leaner in C2H4 with respect to CO2, as is the case in the OCM reactor products. The breakthrough experiments can be reproduced by the RAST, but not by the IAST. This underscores once more the strong non-idealities that are inherent for CO2 capture with cation exchanged adsorbents.